All right, good afternoon. Today we're going to do the 2025 mechanics paper from Edexcel, the A-level version. So let's get started. Question number one, we have some sort of car moving along here. So whenever we've got one of these ones where we've got force diagrams, we can kind of just fill in the rest of it. But seeing here, we've got nothing going vertically at all, and we've got nothing involving friction. If we were to read back up, nothing to do with friction here at all. So we don't really care about the vertical bits. So in this case, what's actually going on, horizontal road, constant acceleration of 2, which is drawn on there. It's got a speed of 15, again in horizontal, and it's modeled as a particle. We want to find the speed 4 seconds after the signpost, after passing the signpost. So constant acceleration, that tells it suvat. So S, U, V, A, and T. Time was 4 seconds. The speed initially was 15. We wanted to find the speed at the end, so we have v is the thing we're looking for, and we also need the acceleration of 2. So no distance in this one, no displacement. So we need v equals u plus at. So plugging that all together, it will be 15 plus 2 times 4, so 15 plus 8 is 23. So it should be 23 meters per second after the 4 seconds. Now we get onto this diagram down here then. So we've got the horizontal forces on the car, mass 800, driving force of D, resistance is 400, and acceleration is 2. So this is just describing the diagram basically. Find the value of D. So when we think about this, if we compare the forces horizontally, what's pulling it to the right is D, pulling it to the left is 400, and that must be equal to its net force. So its net force is mass times acceleration. So it's mass of 800 times by the acceleration of 2. So this side 1600. So if we end up adding the 400 across, our driving force must be 2000 newtons. Lovely jubbly. They both look good to me. At the end, I'll check everything, make sure everything's all right. But if the numbers look dodgy, I'll check straight away. These look fine, though, do you know what I mean? So I'm not going to check straight away. Approach it how I would in a real exam. Number 2 then. So first things first, when I see these questions, angles, I'm going to go up and just write down if sine of alpha is 3/5, cos of alpha is going to be 4/5. You can get that from the triangle. So if we have alpha down here, opposite was 3, hypotenuse was 5. So using Pythagoras, we'd end up with 4 down here. So you can see then cos adjacent hypotenuse gives you 4/5. I know we've already got sine written down there, but I've just got in the habit of always writing them up there so we can just see they're in the same place. You don't have to kind of go looking for it if it's somewhere different than usual. Lovely jubbly. What else do we need then? Let's fit in our diagram. We've got a rough plane, so we'll have some friction going along. That'll put us to the left. And we'll have a reaction force going up as it's on a surface and some weight going down. Its weight then, it's got a mass of 2, so its weight will be 2g. Reaction force, let's just call that r. And our friction force, we could write like just F or FR for friction, but we're always going to use it as mu r. So I'm basically always going to have mu r down there. It's sometimes that we don't want mu r, we just want friction. But in that case, like that's such a rare case that it's easy just to start with this and change it if you need to. So we've got constant speed. That again tells us that this will be mu r. So friction is equal to mu r because constant speed, we're at equilibrium, but we are moving. So we're already past the point of slipping, so it must be at the maximum. That constant speed as well tells us our acceleration is equal to 0. So we know, yeah, we have no acceleration. It's looking good. What do we want to do then? Find the normal reaction plane and describe the motion of the box after we remove that 5 newtons. So over here, reaction force, what we can think about is all we can do really is resolve forces. We could do it either vertically or horizontally, vertically. Could do it in line with this pull motion as well, but that's kind of silly. Horizontal is going to be nice, but it has mu in there and an r. Whereas if we think about just going to the vertical, that eliminates the mu component straight away. So if we resolve forces vertically, let's look at up being positive. We're going to have the r pulling us up, plus some component of this 5 newtons. Thinking that for this side, our angle's nice and cozy, so that's cos. So we're going to need sine of that. So 5 times sine should be 3. And that's going to equal to the 2g we have going down. You could think about this being negative 2g and then equal to 0. So it's an equilibrium. But either way, what we're going to see is r is equal to 3g minus 2. 3g, sorry, other way around, 2g minus 3. 2g is like 19.6, so it'll be 16.6, which is exactly what they want. That looks good. And you can see that equation didn't involve mu in it at all. So because we were perpendicular to our friction, it eliminated the friction. There's no component of friction that's acting vertically. So removed that variable from our equations, made it a bit easier to work with. Next part of the question then. At the instant when B is at the origin, the force of 5 newtons is removed. So describe the motion of the box after the 5 newtons is removed. Well, we're dragging it along. It's moving and it's on a rough plate. So it's moving and then we stop dragging it. It's just going to slow down and stop, like come to rest. So it's going to decelerate to rest. Yeah, if you drag something along, stop pulling it, it doesn't just stop instantly. It doesn't slide forever. It will just slowly decelerate due to the friction. So now, yeah, we removed that force. Let's find the normal reaction afterwards. So this is one thing to be aware of in mechanics. When you change a force or remove a force, all of the reactive ones are going to change as well. So they're all kind of dependent on the other ones that are independent. So yeah, let's remove that 5 newtons. The equations can be quite similar. So it's basically this is just going to become 0. But what we're going to get now is, actually, if we look, yeah, vertically again, we can think about the fact that the 3 is just gone. So in that case, what we're going to have, r minus 2g is equal to 0. So therefore r is equal to 2g. Down the bottom then, what's going on here? So given that after the force of the 5 newtons is removed, we've got a particle, no air resistance, coefficient of friction is 0.2, speed is 4, let's equal some of these actually, 0.2, speed is 4, comes to rest at the point x, find the distance, how far is OX? So how long does it take to stop, basically, as we're pulling it along? Constant speed, does it tell us what that is? Yeah, it did, it was 4, wasn't it? So in this case, what we need to do is use the actual diagram, again, with this 5 newtons been removed, to figure out what the acceleration is. And then that acceleration we will use in a suvat to find the distance. So for the acceleration, what we can think about is, again, resolving forces horizontally. What we've got now to the right, nothing. Nothing pulling us to the right. Remember, our 5 newtons is gone. That doesn't exist, so nothing pulls us to the right. But putting us to the left, we have that friction. So 0.2 times r of 2g, i.e. 0.4g, which I will write as 2/5 of g. And that's going to equal to, again, our net force, our mass times our acceleration. So 2a. What that tells us then, acceleration is negative g on 5. That's good. So like I said, we can take that with a suvat. S is what we're looking for, the distance we travel. Our initial speed is that 4, just the left there. Final speed will be 0. We're going to come to rest. And our acceleration will be that minus g on 5. And here we do not care about time. So in that case, we have v squared equals u squared plus 2as. So plugging these numbers in, or let's rearrange first actually. We're looking for s, aren't we? So it should be the v squared minus the u squared over 2a. So plugging all of this in, v squared 0, minus 4 squared is 16 over 2 times a. So 2 times g over 5. And we have a negative there as well. These negatives will cancel out though. We can then think about this 2, this 16. We can make an 8 and a 1 instead. And times by the 5, what we're left with, 80 over g. Which looks good to me. It's always nice when g's in there still. Like I say, I will double check these all at the end, but they look fine to me at the minute. Last bit of this then is going to be state the limitation of the model, apart from air resistance. Generally you can say spin, but here like it can't really spin, do you know what I mean? It's going to slide instead. So we can say anything about like kind of all these are things that we've assumed are not going to be true. So it's not a particle, it does have some size, do you know what I mean? It will be affected by some sort of size. Gravity is not exactly 9.8, but my answer here includes gravity. So I suppose that we can't include in this case because it's just whatever gravity is. We just plug it into this number. So yeah, probably the fact it's a particle here. So the way that that would actually work in the real world is our contact between, like from us, the object that we have, and the surface would not always be exactly the same. So really our coefficient of friction would like slightly vary depending on how much contact there is between the two objects. So that all looks good to me. Let's keep going to number 3. What have we got here then? Particle of mass half a kilogram moves with constant acceleration of this stuff over here on a smooth horizontal plane under a constant horizontal force of F. Find F in terms of I and J. So we know force is equal to mass times acceleration. So let's take this acceleration, times it by the mass, and we'll get a value of I minus 1.2 lots of J. Part B then, at some time, start time, we have the P is moving velocity of minus 7I plus 7.8 J. Find the velocity after 2 seconds. So thinking about this, again, constant acceleration, suvat. I know it's vectors now, but it still is going to work in the same way. So S, U, V, A, and T. T is the 2 seconds. Our inertial velocity is that minus 7 and 7.8. So I will do this as vectors, like minus 7 and 7.8 in a column there. What we're going to be looking for is the velocity. So that's what we need at the end. And we have our acceleration of 2 minus 2.4. You can see in this case, we don't care about our displacement at all. So V is equal to U plus AT. So looking at that again, this is all vectors in here, well, apart from time, always a scalar. So plugging those bits in, we have the U of minus 7 and 7.8. Our time is 2, and the acceleration of 2 at minus 2.4. So let's go row by row. 2 times 2 is 4, minus a 7 is minus 3. 2 times 2.4 is 4.8. 7.8 take away 4.8 is 3. That again, quite satisfying, they're the same number, probably a good sign that things are looking good. Now find the bearing, or direction of motion, and give it as a bearing. So the fact we're moving minus 3 and 3, let's think about drawing this out. So we're moving, other way around, isn't it? Yeah, we're going 3 to the left and 3 up, 3 to the left and 3 up as well. Let's move that down a little bit. So something along these lines, and we're going in that direction. So this, with it being 3 and 3 and a right angle, is also a right isosceles triangle. So this is 45. So if we think about where north would be, this side is also 45. So if we were to measure kind of all the way around the other way, that's 315. So our bearing should be 315. Spot on. This all good? I think that's all good. So at start of time, P passes through the origin. After 5 seconds, it is at point A. Find the vector from O to A. So basically, where is our what is this thing? A particle. Yeah, where is our particle after 5 seconds? What do we know about it? We know it's constant acceleration. So basically, yeah, it's find the displacement. So using a very similar one to this, or not one to that, to this suvat even. In fact, let's just copy it over. But now our time is going to be 5, not 2. So we can rub that out, put a 5 in, and realize the fact that we're actually, in this case, looking for the displacement and not the velocity. So in that case, not caring about the velocity, we need to have S is equal to ut plus a half a t squared. So in that case, u times t, 5 times all this stuff, 5 times 7 is minus 30, well, 5 times 7 is 35, but we have a negative version. This is 7.8, so 0.8 times 5 is a 4, so that gives us a 39. And then plus a half of t squared, well, that's 25 over the 2 is not very nice. So 25 over 2. And then our acceleration, which we know is a 2 and the minus 2.4. So doing a bit more, let's keep this bit the same, 35 and 39. These halves, so that's going to be 1 times 25 is 25. 1.2 times 25 is 30. And again, negative is still in there. So what we're left with, we've got a minus 10 on the top and a positive 9 on the bottom. That looks good to me as our vector. In terms of I and j then, we have minus 10 i's and we're going to add on 10 j's at the end. Lovely jubbly. That looks good to me. I did this in the lesson the other day. I got a different answer to this one, so maybe there's something wrong there. But this does seem quite nice in like how they do this normally. So this one seems more satisfying than what I got in the exam. So this is one that I will come back and double check at the end. So let's keep going. Number 4. What we got here? So some variable acceleration thing. We've got a position in terms of t, and again I and j's with vectors. So find the position vector when t is 4. So let's just take 4, plug it in. So if we do that, what we're going to get? So on here, if we square root 4, we get 2. Cube it, we get 8. Times that by 4, we get a 32. And 4 squared is 16. So that's minus 16 down the bottom. Find the exact distance. So now that's just Pythagoras on this. So we want to take the numbers that we just found, the 32 and the minus 16, and do Pythagoras on it. But what we can do is actually take out a factor of 16 first, and then we're going to do Pythagoras on 2 and minus 1, which is a bit easier to deal with square and square rooting. So that's going to be 16 times 4 plus 1 all square rooted. So that's going to be 16 root 5. Obviously, you can just use your calculator and do 16 and 32 if you want to, but either way, gets the same answer in the end. Part C then, we want to find an expression for the velocity, give your answer in terms of I and j. So we need to differentiate this. So we do that again term by term. The i's and j's are not going to affect us. So for the first part, we have 4 times 3 half, 3 over 2. The over 2 will take that down to 2, times with a 3 gives us a 6. And the power will drop by 1, so instead of 3 over 2, it will be 1 over 2. We get that many i's. And for the t squared, that'll turn out to 2t, still times by a j. So that's our velocity at time in the future, in terms of t, I, and j. That looks good to me. At the bottom then, what have we got? At some time in the future, acceleration of p is in a direction that is perpendicular to the line with the equation y is a third of x. Okay, so if that's y is a third of x, our perpendicular line goes down here, and it has a gradient of minus 3. So what that tells us is our velocity, whatever we have, if we have 1 there, we need to have 3 on that side, and it must be parallel to that line. So let's go through and find our acceleration. Again, we get that by differentiating the velocity we just found. So if we do that, what we're going to have for the i's, times 6 by a half gives me a 3. Then I have t to the minus a half, and to the bottom, just a minus 2. So that minus 2 is quite nice, because what that's going to tell me is that if I kind of go over this one over here, but with a blue instead, say, I know I have minus 2 on this side. So to keep the ratio correct, like the 1 and the 3 that we have, to keep the ratio the same, this must be 2/3. So that this one is 3 times bigger than this one. Oh, we don't really need the minus there, because you can kind of see I'm drawing it going down. But yeah, this must be 2/3. So the question comes then, when does this equal 2/3? So that being parallel to like 1 minus 3, yeah, it's equivalent to 3 to the t to a minus a half equal to 2 over 3. So what we can do, we can divide by 3. T to the minus a half is 2 over 9. Let's flip it all over. T to the half is 9 over 2. And square everything. So t should be 81 on 4. Seems quite nice again, but is one that I will double check just because it's like the final answer on the question. This is one that we'll come and have a look at again. But nothing here seeming horrendous, do you know what I mean? Like the numbers seem quite nice. Yeah, they do seem quite nice, the numbers that pop out. So if you're getting horrible fractions, horrible square roots, I'd immediately check. But here this seems plausible, doesn't seem too horrendous, so yeah, doesn't seem too bad to me. So let's keep going. What's going to be in number 5? Some projectile something, people chucking stuff off cliffs and that. Yeah, we've chucked something off a cliff. So we're so far in the air, we're going to chuck it 40 meters per second, takes 40 meters to hit the ground. 10 theta is 1 over 2. That's a bit strange. We don't normally have that. So if we were to draw a triangle out, what we've been told there is the opposite is 1, the adjacent is 2. So Pythagoras, 2 squared is 4, plus 1 squared of 1 is 5. So this is root 5. So sine of theta is the opposite there, the 1 over root 5. And cos is going to be 2 over root 5. So that looks good to me. Projectile stuff, it must be suvat. gravity, constant acceleration, always going to be suvat in the end. You can use the variable acceleration stuff, but it just reduces down to suvat. Hence why the suvat's kind of like the shortcut and like the simplified version of it. So what do we want to do? We want to find how far it is in the air and then the maximum height it was at all. So for suvat stuff, all we can do is do suvat. What I'm going to start with is horizontal, mainly because there's no acceleration. So the suvat is actually just speed distance time. So S, U, and T. What can we figure out? We're going to go 40 meters. Our speed is 14 cos theta. So 14 times 2 over root 5. So actually, let's go through and make these in terms of rationalize the denominator on these. So times top and bottom by root 5 there. We should have root 5 on 5. And here what we're going to have 2 root 5 on 5. So think about that, yeah. 14 times this is going to give us, well, 14 times 2, 28, root 5 on 5. 28 root 5 on 5. And t, we don't know. T here is the only scalar. So where we're going to get one equation for the horizontal, one equation for the vertical, all of the values like the displacement, the velocity and the acceleration, they're all vectors. So they have different values in each dimension, horizontal, vertical, whereas the time is a scalar. So it's the same in both. So that will be the bridge between our two different dimensions. So in this case, let's get an equation out. Speed is equal to distance over time. So 28 root 5 over 5 is going to equal to distance of 40 over the time. So we can rearrange that. Time should equal to 28 root 5 over, well, 5 times 40 is 200. We can go then, cancel this off a little bit on our calculator. 28 over 200 gives us 7 over 50. So 7 root 5 over 50. That's the time that this is going to happen at. So that time then, we know that we would travel 40 meters in that time if we have that certain speed. So we can use that then to know that that's how long it would take us to fall to the ground as well. So let's do that now. And I'm actually going to take down to be positive. Reason being is that I can just say that I'm going to travel the value that I'm looking for. I know that I only go up a little bit, but that doesn't really make a difference because overall my net change is going to be this h. So we'll have h as our displacement. Our speed will be the sine component. So just root 5 on 5 times the 14. But it's going to be negative because you can see we're going up here and I've taken down to be positive. So it should be negative 14 root 5 on 5. V we don't care about. A is going to be G. We get positive G here because we're going down. And our T will be that 7 root 5 on 50. So here we don't care about V at all. So we're going to have S is equal to U times T. So minus 14 root 5 on 5 times by 7 root 5 on 50. And then we're going to add on a half of AT squared. So a half of A, which is G, times by T squared. So actually maybe let's do the T squared separately. 7 squared is 49. Root 5 squared is 5. And 50 squared is 2,500. So if we think about that instead, what we're going to get. So this is going to be like 49 on 500. 49 on 500. Does that cancel down? It does not. So that's what we have for that bit. So 49 times 500, all times the G. It's look good. We can obviously just whack this whole thing in the calculator to work it out. That's probably the best thing to do. I will leave it in terms of G though. So G here is in here. It's not in this one. So this I'm actually going to leave alone. It's just going to be 49 on 1,000, not a G. 49G on 1,000. Over here, what's going to happen? Root 5 times root 5 is 5. We've got 5 down there, so they'll cancel out. Bosh, bosh, bosh. We've got 14 times a 7 on the top. That's not going to be very nice with this 50. The 2 can be. So the 2 is going to go. So we'll have 7 times 7 on the top. It's 49. And 2's gone, so that's a 25 on the bottom. Again, that is negative. So there we go. You can see this is kind of the little distance that how far we would have traveled, say we just fired up and like there's no gravity, like the time that it would take us to get to this far, like what's this height basically. and then the negative part is this, like how much gravity has caused it to fall down. So that looks good. Max height of the stone then. Similar sort of idea as what we've done on this downwards one, but we want to have the velocity be 0 at the end, because we can think about it like as you do this journey, the maximum height you're moving completely horizontal, so your vertical component of your velocity must equal 0. So we can take this across. Let's make sure I don't take that 5 at the top. And like I say, just make that final velocity be equal to 0. Doesn't make a difference here about like what I said about up and down sort of stuff. We're going to end flat, so flat is the same if you're looking from the top or from the bottom. So thinking about this, which one do we not care about now? Well, actually our time isn't the same, so this time must go, and therefore that is the one that we do not care about, telling us that we have v squared is u squared plus 2as. We're looking to rearrange 4, in this case s again, because it's not going to be this h. So s should be v squared minus u squared over 2a. So v squared of 0 minus u squared. Let's think about squaring this thing. What we're going to have. So if we actually rearrange this for what it was on the last page, where did this come from? So we've got 14 and the root 5 and 5. So it's 14 and the sine, so it's 14 over root 5. So that is, yeah, 14 over root 5. So that's a little bit easier to square. So on the top we'll get 196. On the bottom we will get 5. And that then is going to go in here. So 196 and 5. And just being a little bit careful, noticing that we've squared it. So the negative did go, do you know what I mean? But we still have that one negative from here. So no matter what, this should have always been a negative term on the top there. Underneath then, 2 times g. Nice and simple, 2 times g. So what do we have in the end? We can times top bottom by 5. We're going to have minus 196 over 10g. If you think about g being 9.8, it's kind of, this is almost like this is 20g. So it's kind of like this is minus 2. It's basically exactly minus 2, because this would be minus 20, 2 times bigger, because this would be, no, minus 2. Yeah, this would be 98 on the bottom, minus 196 on the top, so minus 2. But remember that they are measuring down as positive. So what this means is it actually went 2 meters higher than it started. This tells us like 2 meters above h. Lovely, that looks good to me. Again, nice simple answer. A whole integer answer, always a very good sign. So nothing really sticking out to be horrendous here. This maybe doesn't look so nice, but you often do get not very nice ones here every now and then. So we'll keep going and have a little double check at the end. Number 6 then, we've got some moment stuff. So we've got a uniform rod. Uniform rod straight away then, mass in the middle. So it's going to have a mass of m, g coming down, well, a weight of mg coming down. Particle of 2m is attached at this point. So that's going to be 2mg. And AC is 0.5a. We know it has a whole length of 2a. So effectively, we can split it into 4 equal parts. 1, 2, 3. Well, 1, 2, 3, 4. So what have we got? It's against a rough ground. Doesn't say whether the wall is rough. So rough ground. If you think about it, say you had this as a ladder and you're stood on it, and it was an icy floor. What's going to happen is the ladder will fall this way. Do you know what I mean? You're not going to suddenly like climb up the wall. So friction will always oppose that motion. Our friction will point to the right hand side. Again, we are going to have just mu times r, and here I'm going to have RA come up because the reaction force at A. RB come out the wall here, reaction force at B, and therefore this is mu RA coming up. We could call it friction, but I'm going to assume this is on the point of slipping until they tell me otherwise, in which case I would change it. So this is looking good. Yeah, rough horizontal ground. It's a vertical wall. The rod lies in a vertical plane. That just means it's a 2D diagram basically. Angle of alpha. This should model the vertical wall is smooth. This is R, and this is S. Okay, I will relabel them then. So RA is what they've called R. RB is what they've called S. So this on the bottom, then it's just mu r, not mu ra. That looks good to me. Find r in terms of m and g. So yeah, what the questions are asking for here, that you can do it in lots of different ways, but there's only really certain things that we can actually do. What we can do is resolve forces or take moments to build up equations, which then we solve simultaneously. Where those equations come from is up to you. But generally, when we think about resolving forces, they produce easier equations to deal with than moment ones because they don't have any component of length in there. So we're going to start off by finding those immediately. So if we think about this, what have we got going up? It's just R here, the reaction at A. And going down then, we have the 2mg from whatever object it was at C, and also then the mg from the weight of the ladder itself. So we have 2mg, take away another mg. And moments, for A-level maths, you don't learn how to deal with anything apart it being in equilibrium. So they're always having the point of like the up forces equals the down forces. Or in this case, what we have is that R is equal to 3mg. That's good. I'm not even going to look at the next question. I'm just going to go and get another equation. So if we go horizontally, mu ra, or mu r, so 3 mu mg, and then going left is s. So again, we know that s then is equal to 3 mu mg without even really doing anything else. And then the other thing I can do is take moments. If we look at it, A has two forces coming out of it. So if we use A as the pivot point, these forces will not exist in that equation, only remaining with the other three. And you can see out of those three, there's only one thing we don't know, and I suppose the distance away. So that would give us an equation with two things we don't know. And we can see here, we have another one with two things we don't know. But altogether, how many things don't we know? Oh no, yeah, we do know, sorry, we do know the distance. Ignore me, we do know the distance. So actually, yeah, that equation, the moments one, if we take it around A, involves this, this, and this. The only thing we don't know is S. So that will solve us S straight away. So let's take that equation. So we'll do moments around A, and I'll do clockwise being positive. So we're going to get the 2mg and this mg. We need the components of them that act in this direction. So let's first go and kind of propagate alpha around. So what we can think about, if I draw this line out here, down here, this is not alpha. So if I was to draw this triangle, this one is alpha, because we know that it's just like a similar triangle to the big one we've drawn here. So therefore, if we think about the other side of that, this one is also not alpha. So we're going away from our angle, so we need sine of alpha. So it's going to be, for the 2mg, times by sine of alpha, times by the distance away, so times by the alpha over 2. What I'm going to do is combine that straight away at the front. Sorry, not alpha over 2, a over 2. So just have amg times sine alpha. So that's one term. For the one in the middle then, we have mg again for the strength. The distance away is going to be a, and again we have sine alpha. So they actually, even though there are different strength of forces, have the same moment around a, because one is twice the strength, and one is twice the distance. These two then, we'll add them up, and we'll have to take away any counterclockwise forces, i.e. the amount caused by s. Even easier to see the angle here. We can see that obviously this one is not alpha, must work with alpha to make 90. So this side is alpha. So therefore we need to go with the angle. It's nice and cozy. So it should be S cos of alpha. And this distance away was 2a. And again, these are all equal to 0. As usual, we have a's everywhere. So that tells us our diagram is like scale invariant. You can scale it up, everything would work the same basically. And this looks good. I'm probably going to think, yeah, we can see here, we can get an expression out for S, but we would need kind of more information to find actual values here. I did kind of forget that we don't know alpha. Normally you think like you know what sine and cos alpha are, don't you? But in this case, no. Rearranging for S then, not too bad. What we're going to have, if we added these together, there'd be 2 of them. And we've got 2 here, so that can just cancel out straight away. Just need to divide by cos. So it will be mg tan alpha straight away. Lovely, jubbly. Was that what they wanted? That was what they wanted, wasn't it? Yeah, mg tan alpha. Nice. What's going on down here then? In the refined model, the vertical wall is modeled as being rough. The magnitude of the normal reaction on the ground on the rod at A is R1. State which is greater, R or R1, given a reason for your answer. That's gone right in one and right at the other one. So let's say, okay, now we've got a rough wall. Okay, what's happening to the normal reaction force at that rough wall? So let's think what would actually happen if we did have an extra force there. Let's draw it in, say blue. I'll make it big and chunky so we can see it. So which way would it face first of all? I've got it wrong then. I think, yeah, it's just going to fall down this way. So our friction force would actually be pulling us up. This would be, let's call it sort of mu1s. So where would this add in? It's going to add in anywhere that's pulling up. So here we'd have mu1s as well, sitting us in this place. So would that affect us at all? I don't know. I'm not too sure actually. Let's think, does it affect us anywhere else? It's not going to affect us horizontally. That's not going to do anything. Obviously S is still in there. Maybe that's the case. Because these are still balanced, it should be the same. I'm wondering though, actually, can we see it from this equation instead? So yeah, as we have, this is going to take some of R's job basically. So if we think R affects all of these other bits, so it would change this force, which would change S. Okay, yeah, so that's not affecting it there. So let's think about the moments equation then, because we would have another component down here working alongside it. This is not alpha, so we'd have cos of mu1s. So let's write this down over here. We'd have those two mg sines, a bit thinner, 2 mg sine alpha for the clockwise stuff, and then the anti-clock, so the anti-clockwise stuff would be the 2s cos alpha we had before, plus that new one of our 2 mu s sine alpha. So how does this affect us? If we again rearrange for s, what we're going to have, all our 2's can go away. S will be equal to mg sine alpha over cos alpha plus mu sine alpha. Again, these should all be mu1s really. So how does this affect us? I think in general, what we had beforehand was this equation. Now we have this one. The difference then, if this term, obviously the mu1 being 0 is what's happened. So you can see sine alpha, alpha is between 0 and 90, so sine alpha is positive. Mu1 is also positive, between 0 and 1. So this term is positive. So we're making our denominator larger. So we're making our entire value smaller. So the new one would be smaller. So R1 should be less than R, the original R. So R1 is less than R. Hope that all made sense. You want to go through and see like how does it actually affect it? What new equation do you get out? And it's kind of seeing what's dependent, what's independent. So S is dependent on a few things. So it did change as we added a new force up here. Either that force is kind of like to do with S, that made S change along the way. R would also have changed because obviously like some amount of R's job was to lift this up, and now this is helping it. So R should have decreased as well. This will basically do some of the job of the two reactive forces. That all looks good. We've got another bit over here as well then. So second particle mass 3m is now at the top of the rod. Again, it's on a rough horizontal ground against a vertical wall. Let's say with a bit 3m. We can put our 3mg coming down here. We still have a 2mg over there. Still the mg in the middle. Vertical plane with the wall again, 2D diagram. Linear equilibrium, so it's about to slip. The wall is now smooth. Coefficient of friction is mu. So yeah, friction will come this way. We will go again coming up. I'll keep R and S like they did before. That's R, this should be mu R. Coming off the wall will be S. And again, smooth wall, so no friction coming up that way at all. We're told that tan beta is 1 over 2. So what does that tell us? We had that same one, didn't we, a second ago? That's not beta. So where it's saying tan beta, where did we have that? I'll just go and look at it again. Don't think twice about something. If it can tell you already, within here, wouldn't it? Yeah, so sine is going to be root 5 on 5 because it's double that. Root 5 on 5. root 5 on 5, you are 2 root 5 on 5, lovely jubbly. Find mu. Okay, so again, we're going to resolve forces horizontally and vertically before using moments. So if we go horizontally, what do we get? To the right, we've got mu r. To the left, we've got s. That's it. So they do cancel out with each other. So what we know is that mu is going to equal to s over r. So now if we can get both of those, we've got mu. So let's look vertically. Pulling us up, we've got r. That's it. And then pulling us down, we've got 3, 4, 5, 6 mg. So r is going to be equal to 6 mg. And the last equation to make then is going to be the moments one. So again, we can kind of choose here. We have two different ways to think about it, A or B. Both of them have two forces acting. We know what R is though. So if we go up here and take B to be the pivot point, it eliminates S, eliminates this 3 mg, and then we solve this stuff. That would just solve for mu straight away, actually. That's fine, yeah, that would be fine. We can just solve that for mu. We know what R is. Lovely. My thought was we'd get like some simultaneous equations that we'd solve straight away, but no, that's quite nice. Other way around, we'd cancel this one out. You solve this then for S, do you know what I mean? The other way around, and then plug it in there to find mu. But yeah, let's take it around B then, probably a little bit easier. So moments, where's some space? We'll do it here. Moments around B, being clockwise, being positive. Can be a bit weird thinking from like up here how it's spinning. So let's think about what clockwise means. Clockwise means this way. So R is doing the clockwise stuff. How far away is R? It is 2a away. So we need 2ar. And then let's think about the angles. We have a nice big Z in there. So what we have is that this is our beta in there. And we're wanting to find the one that is perpendicular to our rod. So we need to go away from the angle. So it's going to be sine. Sine is root 5 on 5. That's good. These other three forces then are going to be pulling us in the other direction. So we're going to have to take away, let's start with the one in the middle, AMG. And again, we can do a few other bits. We can see that this, we've got a big F over there. So that's beta. We want to go that direction. Again, moving away from it. So it's going to be sine. So root 5 on 5. Very similar picture for this one. Distance away is 3 over 2, lots of A. Strength 2 mg. And then same angle, all that sort of stuff. You can see here the opposite kind of direction. One is going vertically, this is going horizontally. Where one was sine, one was cos is a kind of a shortcut way to work it out. We can also see, like, as we go down, what we have, this angle down here is not beta. So if we think about drawing that one out, this one is. So we want to be nice and cozy with the angle, give us cos. So that's going to be distance away of 2a, strength of mu r, which we know is going to be 6 mg. We'll actually put that up here as well. Let's do that. So that should be 12 amg in there. 12 amg. And again, yeah, this one is going to be mu r, so times the 6. So again, 12 amg. But this one times the mu, and also times by cos, so times by 2 root 5 on 5. So now we have this equation. Must all equal 0. We can cancel some bits out straight away. What do we have? We have an A, we have an M, we have a G, we have a root 5, and then all of a sudden we're left with a lot less than we did have. So what's up here? Do we have a fifth? Yeah, we have a little fifth everywhere as well. Let's get rid of that. So what we left with, that first one, 12. The next one, minus 3. And then we've got, oh sorry, minus 1 in there as well. And then we're going to have minus 24 mu. That will equal 0. Rearranging this then, mu is going to be 8 over 24. Simplify that down, what do we get? A 1 over 3. And we get a big fat tick, because that is what they want us to have. So that's a good sign. What I'll do is I will have a look. I'll go through doing and double check all these, see them okay. If the video just ends now, that means everything was fine. If the video doesn't end now, it means something was wrong, and I've had to go through and double check. But thanks very much for watching. Hopefully that was useful. I'll try and do some more of these when I have time and stuff like that. So, yep, cheers. Bye. Right, hello, me again. Quick one I got wrong. I just got this fraction upside down. Where I flipped it, I forgot to put t, like it should be 1 over t as this. So our actual answer for t, if we just follow this through, instead of being 7 root 5 over 50, t is actually 50 over 7 root 5. So if we put that in a calculator, rationalize that denominator, 50 over 7 root 5 gives us a nice answer of it's 10 root 5 on 7. So that's our actual answer for t. How's that going to change things then? So that should be over here. 10 root 5 over 7. And that then, if you think about this equation, where did that appear? Actually quite a lot. So it was in this one, u times t, and in this one with the t squared. So again, we need t squared. So squaring this stuff, we'd have 100 times 5. So 500 over 49. 500 over 49, not very nice. So 500 over 49, that is t squared. We can go through and sub it all into here again. So it was u times t. So minus 14 root 5 on 5 times by t of our 10 root 5 on 7. And then we need to take away a half of g. So add on a half of g times by the t squared. So times by the 500 over 49. If we look over here, what's going to happen? So similar things to last time. Our 5, root 5, and a 5. They can all go. You got 140 on 7, so that's minus 20. On this side then, what have we got? We've got a half of 500 is 250. On the bottom will still be 49, and we still times that by g. So that should be the actual answer. Is a bit nicer than what we ended up with. Whether that was, yeah, this thing in here. This seems a little bit nicer than what it was. That looks good to me. So one little mistake, just getting that upside down. That didn't affect the next answer because we didn't need the time for it. Everything else was still fine here. We do get the correct answer of like 2 meters in the air. Spot on. Thank you very much. And there's another little quick one in this as well, where I did part C here, like which one's bigger. I spent the whole time to talk about S, not R. I made the same conclusion. We got the right conclusion, but what we have is the new S is lower, and we do get that same conclusion. Like the new S is lower, so but we had this extra bit, like this is a positive force. So when we think about this new equation, it's R and this force adding it together. So what we have is that R is actually equal to 3mg minus mu1s. So again, this term being positive, we're taking away something positive, so therefore making R smaller. So the new R value is smaller. So we do get that same conclusion again.